Okay, so we were talking about the inverse of the log function. We saw that if we had, well, the inverse of both the log function and the exponential function. But we saw that if we had y equals a to the x, as written as this green line, we can find the inverse of that as y equals log base a of x. And that is this orange line. I guess I should write that. Log base a of x. And I might as well write it as f of x since I wrote the other one as f of x. They're just different functions of x. So notice that this is also the inverse of this log function. This log function is the same function as this function. It's just rewritten, and you should be able to go back and forth between logs and exponents. And there's some practice problems you can work to get that down. And then this function is also the inverse of this function, which in effect is the inverse of this function, but usually we write it in this form. So these two are the inverses of these two. And just as a point of interest, if you have y equals e to the x, the exponential function, then you'll have a log function associated with the same base, y equals log base e to the x, which is the natural log of x. We call that we write that in the shorthand as the natural log of x. That's the inverse of y equals e to the x. Another piece, although this is not typically used very often, this idea. If we have a decaying exponential function, like this purple line, then it's 1 to 1, and it also has an inverse, and that inverse is something like this. So the inverse of a decaying log function is f equals log base a of x. But it's negative. There's a negative in front of it. So that's what flips this around, so it's not up this way anymore. Notice this is a mirror image over this y equals x line to the purple. The orange is a mirror image over that. So if this was y equals e to the minus x, this would be y equals minus natural log of x. Okay, one last topic on log functions. Notice that we cross the x-axis here with a typical log function of this form. We always cross at the same point, 1, 0. Because remember, your exponential function always crossed here. Your exponential function always crossed here at 0, 1. So it's going to be the inverse of that. And this function never touches the y-axis. So x is not allowed to be 0. In fact, it has to be greater than 0. And that's the domain of our log function. X greater than 0 is our domain. And our range of our log function is minus infinity. So this goes to minus infinity. The closer we get to 0, the closer this gets to minus infinity. It can never reach minus infinity because we can never ever reach 0. Is less than y is less than infinity. As x gets infinitely large, y gets infinitely large. So that's the range and domain of your log function. So because you have that restriction, when you're programming, you need to be careful when you're programming with log functions. You need to make sure that the value you send as the argument, say you're dealing with a natural log of something in here, this has to be greater than 0. Whatever you send there has to be greater than 0, because the computer's going to send you back an error message. It might not tell you exactly what the error is, but yeah, you're somehow sending an argument there that is less than 0. So let's say you have maybe natural log of x plus 2 as your function. Well, then your domain, your x values that are allowed, means that, again, this argument has to be greater than 0. So that means that x plus 2 must be greater than 0, or x must be greater than minus 2. And that makes perfect sense. If you stick minus 2 in here, minus 2 plus 2 equals 0. You're not allowed to have a log of 0. And if you stick a number in here, like minus 3 plus 2 is negative 1. Well, now you got a negative number in your log function, and it doesn't work, so it's not allowed. So that's how you can calculate domains, like if you're programming. Just set whatever your argument is equal to 0 and solve for x.